quantum devices, please.
Good morning, everybody. Thank you very much to the organizers for giving me the chance to talk here, especially Rodrigo and Alvaro. I'm also a frequent visitor of this place. I think this is the fifth time I've been here in 2 years. This year, in the beginning, I was here for 3 months, as Rafael was mentioning, and so I feel a little bit at home here. So I'm gonna talk about something connected to what Rafael was saying, but slightly different at the same time. It's connected because it's about certification of devices, and here I will focus on the many-body regime, right, where you really have system with many particles. So I think I have a problem with this. Wait. Hold on. Okay. Doesn't seem to be working. Oh. Okay, the old trick of switch it on. So yeah, okay. Good. So I would like to motivate my talk with the 2 slides, with a little overview of the advance of many-body quantum technologies. Now I'm going to be talking about many-body quantum devices. So here we can see, for instance, so there's been an impressive advance in technologies, right? So here we have experiments being run with linear optical tables with 6, 8, and up to 10 entangled photons. We have the Gaussian regime, where people do already demonstrate entanglement in Gaussian states of thousands, tens of thousands of photons. And of course, we have this new trend, this new technological trend of integrating linear optical tables into chips, right? And this is on the optical side. So we have also, okay, what's going on here? Is it possible that it has little battery? Okay. Okay, thank you very much. So here, this is on the side of opticals, of atomic systems, right? So we have lots of advances also with ion traps, where people are doing entangled states and quantum simulations with tens of ions. Of course, we have cold atoms in optical lattices. Now we also have on-chip superconducting qubits, and there's many others. So including, for instance, the recent many-body experiments with Rydberg atoms. So I'm going to be talking a little bit of that. So the question that I want to address here is, so how do we trust the quantum devices we build, right? So I mean, the idea of the whole point of quantum simulations is to do things to solve problems that cannot be solved with the classical computers that we have. No? So the question is, okay, so then if we're going to be trying to do things that cannot be solved or predicted in any efficient way with classical machines, then how do we know that the experimental quantum simulations that we're doing are indeed working fine? How do we know that they're actually solving problems that we cannot solve in a cheaper way with classical machines? So this is connected to the question, for instance, that was discussed about so the D-wave experiment. So right, so that's a typical example of a certification problem, where a company sells you a many-body quantum machine, and then you ask yourself, is it working fine or not, right? So that's the question that I want to address. And I see 2 points why this is important. So one is more fundamental, and I like to quote this paper by Dorit Aranov and Umesh Vasirani. So from quantum computing, we know that that simulating many-body quantum systems is exponentially complex in a classical machine, right? So ultimately, the question about certifying a many-body quantum system is also about testing quantum mechanics in a newly available regime of high computational complexity, right? So this moves us away from the paradigm of the philosopher Popper, which is the basis of the scientific method of predict and verify, right? So here we cannot predict the behavior of the outcomes of measurements on many-body quantum systems, right? So if I in general a many-body quantum system or a quantum, well, also a universal quantum computer, and then I ask you, for instance, to predict the outcomes of the measurements. So say, I don't know, you have an so for instance, one of the simplest examples that we know, you have an optical table with photons, right? So you start some of the modes in photons with population 1 and all others in the vacuum state. And then you let the system run through a linear optical table with beam splitters and phase shifters. And then in the end, you measure photo detection, right? If I ask you to predict the probability distribution of that outcome, you cannot do that classically, efficiently. It would take you a time that goes exponential with the number of modes, right? So in general, so that's what I mean. So quantum computing teaches us that we cannot with a classical machine in general predict the outcomes of measurements on a many-body quantum system, right? And this also applies for expectation value of local observables in general. There are only few models where we actually can predict things efficiently with a system size. It's all a matter of efficiency here. Of course that for small systems you can always diagonalize the Hamiltonian and predict everything, right? But we're now reaching the point of we're doing experiments with 40 or 50 spin 1/2 particles. So the size of the basis of Hilbert space is 2 to the 40, 2 to the 50. And then if you want to do non-trivial things there, it's very expensive computationally on a classical machine, right? So that's what I mean by that. So now if I tell you, okay, let's model our system, okay, of course you can make thermodynamical predictions, but now I'm talking about detailed quantum control. If you want to do predictions with a level of detail that we want to do in quantum simulations for 50 or 60 ions, it's very difficult, right? No, sure, it's not a matter of principle. But what I'm saying, okay, so I like that because my aim was to provoke you a little bit with that slide. So, yeah, so what I want to say, so what I like about the other slide here is precisely that I mean, I'm not here to say that quantum mechanics is false, but also it might be the case that at some point there will be something beyond quantum mechanics, right? I mean, at some point we will succeed in the unification of gravitation and quantum mechanics and relativity, for instance, right? So there might be some advance, some other thing afterwards, right? So the confirmation that we have at the experimental level for a few qubits is tremendous, that quantum mechanics is correct. So one might expect that if there is some departure from quantum mechanics, this might happen at the high energy regime of many particles, for instance. So if you want to do predictions with detailed level of quantum control for many particles, then you can't with a classical machine. You simply cannot, right? So that's all I'm saying, okay? Because of the complexity of the computation. But yeah, it's technical. But the thing is that if there is a failure of quantum mechanics, it might be the case that it's in the high computational regime of high computational complexity regime of quantum mechanics. Okay. Easily falsifiable. Why? Well, how do you falsify it? So again, I insist, you make a measurement, you make an experiment to try to falsify it, right? And this experiment gives you some result. And this result, how do you know if it's correct or not? That's not what I call I mean, so again, so I insist, for small systems, you can always diagonalize the Hamiltonian and you can simulate that classically. What I'm talking now is of regimes where you cannot simulate things classically, and then you have a machine, you build a machine, a quantum simulator, and this simulator gives you some result, and then you say, is this correct or not? I don't know. I don't have anything with which to compare. I don't know. I cannot even classically reach the prediction of quantum mechanics. Okay, but we can discuss that later. This is just motivation. Okay? So so I succeeded with my motivation. I think that people are motivated now. So of course, one of the first things that appeared was quantum state tomography, right? So the process of quantum state tomography is the following thing. You have an experiment, you run an experiment, you make an experimental preparation of a state, and then you make measurements, for instance, of log observables on your system, right? And based on the statistics of those measurements, you make a full reconstruction of all the elements of the density matrix of the preparation. The thing is that it's very, very expensive, right? So for instance, here I show, so this was one of the most impressive experiments of tomography. That was already 12 years ago, and this is already like the state of the art. So this state tomography has an advanced much in these 12 years. So this is an experimental reconstruction of an 8-ion, of an 8-qubit. This was in Innsbruck. This was in the ion trapping group of Reinerblatt. The first author is Helmut Hefner, who's now in Santa Barbara, right? But so this was one of the most impressive reconstructions of an experimental state of 8 ions. And the thing is that it is very expensive. You have to do an exponentially large number of measurements of different observables, and also it's terribly expensive to process the statistics that you get afterwards, right? I mean, what do I do afterwards with a 2 to the 8 times 2 to the 8 density matrix? Any information that you wanna extract from that is very difficult, right? So this is not a scalable option, right? So I think it's a couple of hundreds, but I don't remember. But I might be unprecise with this. I don't remember, right? So yeah, so this is also a different issue, right? So here, I don't have time to enter into what's called the sample complexity of estimation. So there are two things why certifying an experimental state of many-body devices can be difficult. One is because you have to measure many different observables, and the other is because of statistics, that perhaps for each observable you have to run the experiment lots of times to collect enough statistics, right? But I won't have time to touch that subtlety today, but it's a relevant question, yeah. So we think that certification is one of the bottlenecks for moving for proof of principle quantum simulators into really non-trivial and reliable quantum simulators, right? So we have two motivations. One is more fundamental, and the other one is more practical, right? So today, okay, so, well, I think I'll advance a little bit faster because that has been already enough motivation, and I want to go to the outline of my talk. So today, I'm going to give you a flavor of some works that we've been doing over the last 2 or 3 years on something that's called fidelity witnesses. So the whole thing here is to search for the cheapest certification paradigm. So as I was mentioning, quantum state tomography is very expensive. This is not the way out when you move to many particles. So here, I want to go to the cheapest certification paradigm in terms of experimental resources. And this is, as far as we know nowadays, is something called fidelity witnesses. And I'm going to try to give a flavor for bosonic fidelity witnesses for bosonic quantum simulations. In particular, I'm going to focus a little bit on Gaussian states, and then I will move to the certification of a class of fermionic quantum simulators, which is simply free fermions that is very well known in condensed matter, right? So as I said, in search of the cheapest certification paradigm. So there are different things. Oh, okay. So first of all, let me tell you what is a figure of merit that I will use to get convinced that my device is working properly. So the figure of merit that I'm going to use is simply the fidelity. So in all the rest of the talk, I will be talking about 2 states. So here, rho t is something that I call the target state. So I want to do an experiment where I want to prepare a state, which is the target state rho t, that I know. And it's typically a pure state. And then rho p is the density matrix that describes my experimental preparation, which is totally unknown, and in particular mixed, possibly mixed, right? So it happens that the fidelity between 2 states, it measures how close these 2 states are. And it's simply, when one of them is pure, it's simply the overlap, right? So here, if rho t is a pure state, it can be written in terms of state vectors psi target, psi t, and then you can simply calculate the overlap, right? So that's what I'm going to be, that's a figure of merit with which I'm going to be measuring if 2 states are close or not. And this is a figure of merit that people like in quantum information because it measures the probability of doing a measurement on your preparation and getting an incorrect outcome. And you can also relate it to a more mathematical distance, which is the trace distance. But given the figure of merit, then the mindset that I'm gonna be considering is a typical mindset of computer science, where you have two guys. One is the quantum prover, Merlin, who has, for instance, a very powerful quantum computer here, and then also the Arthur, no, the mortal. So Merlin is a magician that is very powerful, and Arthur is almost classical. So he has just a classical computer, right? And also he has some measuring capabilities, some quantum measuring capabilities. So that's why I say that it's almost classical. He doesn't have just a classical computer. He has classical computing processing power, but also he can make measurements. So for instance, he can make measurements of single modes or single qubit devices, right? So the typical instance, so this is called non-interactive because there are more complex schemes where they interact, they exchange information. But here I'm going to be focusing on the simplest one, where he simply sends to Merlin a description of the target state that he wants and the number of copies that he wants, and then Merlin, almighty Merlin, he prepares that and sends it to him. So this is a bit complementary to what Rafael was talking. So today Rafael was saying that device-independent scenario is where you don't trust your measuring capabilities. So here, Arthur trusts his measuring devices, but he doesn't trust the preparation that the prover prepares, right? So here, the black box is the quantum computer that the prover has here, right? Yeah. No, here I'm assuming that he only has local measuring capabilities, right? So measure if it's bosons, he can measure quadrature operators, for instance. He can measure homolining, or if it's qubits, he can simply measure Pauli matrices for each qubit, right? Yeah, yes, it's an important assumption. The more quantum power you give to him, the easier the certification becomes, right? But here we try to model the situation that you have in the lab, where you sort of measure local observables and correlations among them, right? So as I said, so in full state tomography, what you ask is, okay, given a pure state rho t that I know and an absolutely unknown rho p, you ask yourself, okay, where exactly is rho p? That's what full state tomography gives you. It's a total description of rho p. Then there are other techniques that simply, they don't know, so they don't give you information exactly of where rho p is, they just give you information of how far away in terms of fidelity rho p is from rho t. So it's less information. And an even more practical scheme that you can imagine is, okay, I don't even want to know how far away rho p is. I want to know if, given some threshold fidelity ft, is rho p closer or further away than that? It's a single bit question, right? Yes or no? That's kind of like the least information that you wanna extract from your system, and one expects that that's cheap also from in terms of experimental resources, right? So from that least scheme, so let's say the most practical thing that that you can do is say, okay, then I would like to have a scheme that is able to tell me if that is able to reject all preparations that are in this red region and that at least accept ideal preparations, right? So it happens that in practice, because of continuity, typically if you ask that for a scheme, you will automatically have this. I mean, you will have a scheme that rejects all invalid states, but accepts like a ball of states around your target state. And that's precisely the cheapest scheme that we look at. So this is the main tool here is fidelity witnesses. So what is a fidelity witness? A fidelity witness is an observable W, right? So again, here this is a pictorial representation of the set of states. Here is rho t, the target state that I know. It's a pure state, so it lies on the boundary of the set of states. For those that know the geometry of the set of density matrices, but for those who don't, doesn't matter. Believe me. So if rho t is pure, it lies at the boundary, at the exterior boundary of the set of states. And here is a ball. So by green, I represent all the states whose fidelity is larger than the given threshold fidelity that I choose. Now, say that I choose ft to be 0.95. Okay, and then a fidelity witness, what it does is an observable that sort of splits the set of states into two halves. One in which all states are valid, are close to your target state, and the other one you have the invalid states, but also you sacrifice some valid states. You do that for the sake of experimental efficiency, right? So the definition of what we understand by fidelity witness is an observable such that for a given target state, so it gives you one if and only if your preparation is ideal, namely it's equal to the target state, and also it gives you a lower bound in general, right? So the expectation value of this observable gives you a lower bound of any experimental preparation with respect to the target state. That's what we call a fidelity witness. So now let me give you a flavor of what is a fidelity witness for bosonic systems, right? So here, so for instance, I'm talking about, so we have efficient fidelity witness for the following classes of states. So first of all, the Gaussian states. So the Gaussian states can be thought of as the following. So imagine that you have M modes, and all of them prepare in the vacuum state with no photons, and then you apply some Gaussian unitary that has squeezing, for instance, and this is a general Gaussian unitary, and this defines our target state rho t. Then you can have a different type of experiments where, for instance, instead of starting all modes in the vacuum in the beginning, you start some of them, you start n of them with one photon, right? You start with a Fock state with one photon in each of these n modes and 0 photons in the following m minus n ones. And then you apply a passive unitary, which is simply a collection of phase shifters and beam splitters, right? You can also have more complicated thing where you do post-selection here, but I will not have time to describe that. I just want to tell you that we're able to have efficiently measurable fidelity witness that cover all these type of experiments, which is essentially all the experiments that people do nowadays in the lab. So I'm not going to have time to go through the technicalities. I'm going to just show you the simplest case for Gaussian states. So for Gaussian states, as I was saying, you can represent any pure Gaussian state as the vacuum state of M modes sandwiched with a general Gaussian unitary, right? And then the fidelity of this target state with respect to any unknown preparation rho p can be written simply as the trace as the overlap of the pure state with rho p. And then, of course, I can swap around this u because of the cyclicity property of the trace. I can simply take this u to here, right? So here, this twiddle rho p is simply the Heisenberg representation of rho p with respect to u. So then I can use a bound that is known, and it's very simple. So I can simply, so this inequality here is an operator bound. So this has to be understood in terms of matrices, right? So what I'm saying here is that the projector onto the vacuum is always larger or equal than the identity minus the total number operator of the M modes. This means that if you take the expectation value of the left-hand side with respect to any state, it will be larger or equal than the expectation value of the right-hand side with the same state, with respect to the same state. With that, you can get, I mean, it's easy to get convinced that this bound is good. With that, you can derive a bound to the fidelity, which has the properties that we wanted for the fidelity witness, right? So here, our fidelity witness is simply this observable here, right? Which is the identity minus the total number operator sandwiched by the unitaries, right? So it's very simple to get, it's very easy to get convinced that this is a valid fidelity witness. So for instance, if in the trivial case where U is the identity, well, this will be related to the average number of photons of your state, right? So if the average number of photons of your state is very low, then you have confidence that the experimental preparation is close to the vacuum state. That's an extremality-based argument, right? It's a very simple argument, but very powerful precisely because of its so there is a question of, okay, so how can we measure this, right? How do you measure in the lab? So you can show that you can measure that in going to phase space representation. So you run something called homeline detection, and then you can actually measure. You need to measure only quadratically many quadrature correlators, right? So expectation values of Q of one mode times P of one mode of another mode, where Q and P are position and momentum, right? So it's kind of it's remarkable because you can certify a totally unknown density matrix with only quadratically many measurements, quadratically in the number of modes. I'm not going to have time to show you exactly how this works. I would like to devote some slides to the more recent work that we've been doing for free fermionic quantum simulations, which cover many paradigmatic spin 1/2 systems. How much time do I have? 20 minutes, excellent. Okay. So So okay, so what are these? So people in quantum information call these free fermions fermionic linear optics, right? So this is a bit strange. No, I mean linear optics is something that we know from photons, and now that we use this language for fermions, it's a class of states or yeah of systems that include many important physical models that are under experimental investigation nowadays with quantum simulation technologies. So, for instance, many spin 1/2 chains with nearest neighbor interactions, including, of course, the XY model and the Ising model that were mentioned today, belong to this class. There are some tight banding models of condensed matter physics and certain bosonic systems, and even some two-dimensional lattices, which is this Kital's honeycomb, for instance. They all belong to this class of free fermions, right? And people in quantum information also call them Gaussian fermions or fermionic linear optics. I didn't invent these names, so this is the nomenclature that people uses, and they have many interesting properties. So one of them is that they encompass long-range correlation. So there is a problem. So typically, in many experiments, the more entangled or the more long-range entanglement that you have in a system, the more difficult its certification becomes. But for this restricted class of systems, so they have a form that I will show you, but they encompass long-range correlations, right? So you can certify with this technique that I'm going to show you, you can certify experimental preparations of state that have lots of long-range entanglement. So this is a cool thing, and of course the thing about this is that they are simple from the point of view that they admit an exact analytical solution. So then, of course, you could ask me, what is the point of certifying a quantum simulation of a quantum system that has an exact analytical solution classically? So the point is that people are using this spin 1/2 chains as like a benchmark test for quantum technologies. Since the systems in the target systems that they want to simulate here have an exact analytical solution, then they try to run a quantum simulator to model those systems and to compare, so to have a mean to compare. But as I was saying, the fact that you have an exact analytical solution of a model does not imply that one can efficiently certify its experimental simulation in the stringent sense that I'm talking about, fidelity, right? So let me introduce you this fermionic linear optics, and it's very similar to the Gaussian regime, to the bosonic Gaussian regime that I was mentioning for photons. So imagine that you have a chain with L spinless fermionic atoms, right? So this is an abstraction. Of course, atoms to be fermions need to have a semi-integer spin, but here I don't want to talk about the degree of freedom of spin. Here I simply want to focus on L particles that have annihilation and creation operators that satisfy the usual canonical anti-commutation relations. And then you can go to the Majorana mode picture. This is not necessarily the only way, but it's useful to do it because it resembles a lot what happens for bosonic Gaussian states. So you go to this representation where you now have mode operators M, and again, you have L sites, and for each site, you allocate two mode operators, right? So here, for site J, I allocate a mode operator 2J minus 1 and 2J, and both of them are simply defined as the sum and the difference between the annihilation and creation operator. So they're very similar to the momentum and position quadrature of bosons, right? Momentum and position quadratures of boson are defined in terms of the sums and the differences of the photonic creation and annihilation operators, right? So this is analogous for fermions, so we define a fermionic so an even fermionic system. So an even is a technicality, but let me focus on the fact that it's free or Gaussian or linear optical. These three things are used interchangeably in quantum information. So we say that a system is free if it's governed by a bilinear Hamiltonian in the mode operators, right? Where A is some coupling matrix, some real coupling matrix of size 2L times 2L. And the nice thing about this system is that, as I said, they admit an analytical solution. So you can actually describe how these mode operators evolve in time. And they evolve linearly, right? So given a fermionic Gaussian unitary, which is defined as the exponential of one of these Hamiltonians, you can show that evolution of these mode operators is simply linear, right? So mode j at time t is a linear combination of all the modes k at time 0. And you know who these linear coefficients are. So qt is the representation of ut in mode space, right? So here is Hilbert space, here is mode space. Here is exponentially large dimension, here is linear dimension in the number of modes. So these Majorana modes may seem something artificial, something abstract, but they are connected to qubit experiments, to spin-1/2 experiments through something called the Jordan-Wigner transform. I don't want to enter into too much technicism, but can define if you have L qubits and they all are associated to Pauli matrices Z, X, and Y, by multiplying products of Z's and Y's and X of the different qubits, you can define these Majorana modes. You can verify that these products of Pauli operators satisfy the same anti-commutation relationships as the Majorana modes. And you can see things of this form, for instance, right? So, for instance, I was advertising that, for instance, this XY spin-1/2 chain belongs to the class of fermionic system, of free fermionic systems, and this is because of this fact. It's because each of the terms here can be written in terms of a quadratic expression of the modes, and therefore you can take it to the form, to the bilinear form that I was showing for free fermionic systems, right? So this is just to show you how, for instance, you recover an experiment with spin-1/2 particles in this free fermionic representation, right? So now I will show you how the fidelity witnesses for the whole class of free fermions looks like. Okay, so again, an arbitrary L-mode pure fermionic Gaussian target state, so an arbitrary pure free fermionic target state, can be written as some Fock state, right? So here's so this is psi target, right? So rho t is written in terms of state vectors, pure state vectors. So U is the fermionic unitary. W is a Fock state, which simply tells you what's the population. So you have an L, so a string of L bits, zeros and ones. Simply says, is there a fermion or there is not a fermion? You can think of that as a lattice, as an optical lattice, where there is or not an atom. Or in the spin representation, you can simply relate it to spin ups and spin downs. So for this Fock state, I can define like a locally flipped fermionic occupation number. So here notice that if all Wj's are 0, then this NW is simply the sum of all Nj's. So this is nothing but the total occupation number. But when I have some 1 here, so one populated fermion, then I simply flip it here, so in such a way as to obtain an observable such that my Fock state is the 0 eigenvalue eigenstate of this observable. Right? So it's simply a construction in which I sum all the number operators of all the modes, and I locally flip them depending on the population of my target of the Fock state that defines my target state. So why do I do that? Because then I can recover something that is very similar to what I was showing you for the bosonic case. So for instance here, so today for the case of bosons, if you remove this W here, you obtain the same fidelity witness that you had for pure bosonic Gaussian states. For the fermionic case, you have more freedom. You have this Fock state here, and this is how the fidelity witness looks like. And now, for instance, if you write this number operator in the Majorana mode representation, you can see that it's a quadratic function of the modes. So this means that this NW is also a quadratic function of the modes. That this means also that this guy here is also a quadratic function of the modes. So why is this important? It tells you that this fidelity witness, again, is quadratic in all the mode operators, but the mode operators are only 2 to the L. So you have an expression, a quadratic expression of 2 to the L observables. So this means that to measure this observable, you need to measure at most quadratically many observables. And this is very powerful. So I reset a little bit, right? So we have an experimental preparation that lives in dimension 2 to the L, and we're able to to certify it unconditionally without assuming anything of the preparation by measuring only at most quadratically many observables, right? And in fact, in most cases, when we have, so for instance, when we have systems that satisfy an area law, so for instance, if you take ground states of local gapped Hamiltonians, then you know that it's even less than quadratically many. So this is what we call efficient in the computational complexity sense. Yes? Sorry? So that's a good question. The answer is no. So again, so this is a good point. I'm happy that you asked that. So it's the target state that I assume that it's free, that it's a free fermionic system. When I say that the certification is unconditional, I mean that the preparation is totally unknown. If, of course, if you assume that the system that you prepare is indeed described by a density matrix that belongs to the set of free fermionic density matrices, then the certification is very easy. So here, we don't want to assume that, right? I don't assume anything of, you can have any quantum noise, any preparation, so anything, right? So you give me a black box, I don't want to assume anything, I just know that the target state that I would like to prepare belongs to this free fermionic class, but I don't want to make any assumption on the preparation. That's what we call unconditional certification, right? But thank you for the question. So who are the observables that you have to measure? Well, as I said, so for instance, in trapped ions or in cold atoms or in Rydberg atoms, then these are simply products of Pauli operators, right? So what I hope I have time, let me see to, yeah, so for instance here, I wanted to devote just 2 slides of possible applications of this technique, right? So here, this is the experiment that appeared a few weeks ago in the archive. This is the MIT and Harvard group, where they prepare something that I think is the record of quantum simulators. So this is a 51 Rydberg atom simulation of an adiabatic passage across a phase transition. So here, what I try to represent. So for instance, here is the ground state phase diagram. So this is a transverse field Ising Hamiltonian with tunable interaction. Imagine that I start my system of 51 spins with a very intense transverse field. So all the spins are aligned with the transverse field. So this is what you can see here, right? So red and blue stand for up or down here, for instance, right? So all the spins are pointing up. They're aligned with your transverse field. And then adiabatically, you start increasing the strength of interaction. So these are Rydberg atoms trapped in an optical lattice. Yes. 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 Yeah. So what I wanted to say is that so initially, like you start with all the spins aligned with the field, and then you make the interaction increase, which is here based by some detuning parameter because of the optical lasers that you use, and then you go to an order phase, to a crystalline phase. So for instance, here, if the interaction Hamiltonian is nearest neighbor, then you start with all spin aligned with the transverse field, and then you end up with a final state that is still a product state, but where you have a periodicity. Now it's up, up, down, up, down, up, down, right? So this is what they call the crystalline phase, and here you can see it, right? So initially you start in this so-called disordered chain, and finally you arrive at this other state where you have this periodic ordering of the spins. And now they measure the fidelity with respect to the target state that they expected, and they can do it because the final state is very simple, right? So here, the final state is just a product state. It's just the periodicity, right? But the final state that they expect is very simple. So the target state is very, very simple. It's a product state. For us, with this fidelity witnesses for free, so this system here for nearest neighbor interactions belongs to the class of free fermions, which means that for us, it doesn't matter. So for instance, they could stop in the middle or close to the phase transition where there are lots of long-range entanglement, and we could certify that efficiently, which is unattainable for them. They can only certify the final state because the target state that they experiment, so they can only certify the experimental state just because the target state is a product state. For us, this wouldn't be a problem. Okay, so this is one example of possible applicabilities of this technique, and the other one example that I wanted to show is an experiment from last year, from the Innsbruck experiment in Austria, and so here they run something different, right? So again, now here they have like 14 ion simulation of a sudden quench. Rainer Blatt is the leader, but Christian Ross is the one running all the quantum simulations experiment. Yeah. So so here is a different thing. In the previous slide, I was showing you an adiabatic passage across a phase transition. And here, you start again with all the spins aligned with the transverse field, but then, bang, you kick the system, you change the Hamiltonian parameters very quickly, and the system starts to run very strongly out of equilibrium dynamics. So it starts to oscillate. You're out of the adiabatic regime. It happens that in that situations, you develop lots of long-range entanglement. For those who know the Robinson bound, you know that that correlations propagate through the system linearly with time, right? So here they run something that is called matrix product state tomography, and it happens that as time increases, long-range correlations develop, and then matrix product state tomography becomes more and more expensive, up to the time that if you want to, so here, for instance, you can see that like K is the number of blocks that they measure. So matrix product state tomography is based on tomography of local blocks. So for instance, for small times, it's enough to run local tomography of very small blocks of reduced systems of size 1, 2, 3, and 4. But you see that as time increases, if you want to keep a high fidelity, you have to, it becomes more and more expensive, right? So here we can see the growth of entanglement. So this is the block entropy, the von Neumann entropy of the chain as time passes by. So again, for us, this wouldn't be a problem, because for us, time here doesn't matter. We can, so for instance, here you can see a simulation of something that is called a covariance matrix in this Majorana mode representation. So it's simply something that tells you the evolution of the modes. And here you can see, for instance, a simulation with 100 spins, and for a long time, where long-range correlation have already propagated through half the system, and this always belongs to the class of free fermions, so we can certify it only with quadratically many observables at most, which should be compared with this that becomes exponential when time increases, right? So, so with this I come to my conclusion. So we're now in search for the cheapest certification paradigm, and we fall into this thing, hypothesis testing, this weak membership problem. The stars here are these fidelity witnesses that sacrifice valid experimental preparations for the sake of efficiency. So I talked about multimode Gaussian states, fidelity witness for certification of multimode Gaussian target state, and also for free fermionic target state. And I think that these are efficient tools for benchmarking of experimental quantum simulations. That's the main take-home message that I would like to convey. I would like to finish with some overview of the field. So, of course, it would be interesting to go beyond integrable models, and this is a big open question. I'm by far not a specialist in condensed matter, so I know very little about such things. But from the point of view of quantum information, we would like to go beyond. This doesn't seem to be so simple. Also, there is something that I am assuming throughout, which is independent and identical distributed preparations. So we would like to go beyond that. And for discrete dimensional system, there is something called the quantum definitive theorem. So more or less, we imagine how to do it. But for continuous variable systems, there's no such thing. And then, of course, there are some crazy ideas of using machine learning to define fidelity witnesses. And also, I mean, in the end of the day, we would like to have like an efficient technique to certify Fermi and Bose-Hart models, right? And of course, you might say, well, perhaps you're not interested in the fidelity. The fidelity is a bit too much. Perhaps there, you're only interested in certifying that the expectation values of the local observables are close to what you expect or not, right? So we don't know how to solve these systems in general, but there is hope someday we can derive efficient certification schemes for that. I would just like to finish with so this is a work that was triggered when I was a postdoc in the group of Jens Seisser, who's here. So Jens Seisser is the first author of the review of modern physics on area laws that was mentioned this morning. And my collaborators that started this are Martin Klisch, Christian Roos, Christian Gogolin, and Marek Glusa. And then, so now I am based in the Federal University of Rio de Janeiro, in the group of Professor Davidovich. There are many people there, but here I'm just showing my sort of, let's say, the core of the group with whom I collaborate. So Carolina is just, she's a master's student. Also Renato, Eric is a PhD student. Marcio is a postdoc there. Ranieri is half experimental, half theoretician. He's a student of Professor Stephen Walborn, and I am co-supervising him. He's also the guy that did one of the experiments that was mentioned today in the talk of Rafael Chavez. And with that, now I would thank you for your attention.